Welcome back. So today, we're jumping into a story of engineering on a scale that is just, well, it's hard to even wrap your head around. We're going to break down how Uber built a system to handle a flood of data that would literally break most of the internet. So, let's just get right to the headline number.
And when I say scale, I mean this. 150 million reads every single second. Just think about that. Every time you or millions of other people check a price, look at a map, or hit that request ride button, it's firing off requests just like these. So the question is, how on earth do you even begin to build something that can withstand that kind of pressure?
All right, so here's how we're going to trace this whole engineering saga. First, we'll look at the initial crisis they were facing. Then we'll see their first brilliant solution, this massive shield they built. After that, we uncover a hidden, spooky flaw in the system. Then comes the breakthrough moment where they solve it. And finally, we'll see the absolutely mind-blowing results. Let's dive in.
Okay, so every great engineering story starts with a problem, right? Well, Uber's problem was that its own incredible success was about to take down its own infrastructure. They were facing a true crisis of scale.
You see, at the heart of Uber's data infrastructure is this system called Docstore. It's built on the incredibly reliable MySQL. But here's the thing. Even with the fastest hard drives in the world, there's a physical limit to how fast you can read data. And at Uber's scale, they were slamming into that limit hard. The system was just hitting a boiling point. It was getting way too expensive and honestly, just too slow to keep up.
And to really understand the stakes here, look at this. They had two paths. To handle just one of their major services directly from the database, it would have taken about 60,000 CPU cores. Just imagine the cost of that. But the goal, using a different approach called caching, was to handle that same fire hose of traffic with only 3,000 cores. That is a 20 times reduction. The choice was a total no-brainer. But actually pulling it off, that was the hard part.
So what even is caching? You know, the easiest way to think about it is like your brain's short-term memory. Instead of having to dig deep into your long-term memory, which is like the database, for a common piece of information, you just keep it right at the front of your mind, ready to go. It's a super fast, easy-to-reach layer for the data you use all the time. And this concept? This was the key.
And that brings us to the hero of our story, a system they called CacheFront. This was Uber's first big attempt to build a unified, integrated caching solution designed to act as this massive shield, protecting the main database from that insane request volume. So the logic they used is actually pretty simple and really elegant. It's a classic strategy called cache aside. Here's how it works. A request comes in, and the first thing the system does is check that super fast cache. If the data's there, boom, that's called a hit. It's sent back instantly. If it's not there, that's a miss. No problem. It just goes to the main database, grabs the data, and then, and this is the important part, it puts a copy of that data into the cache so it's there for the next time. And you know what? It worked. The results were absolutely staggering. CacheFront version 1 was a massive success. It was handling over 40 million reads per second on its own, shielding the database from almost everything. Performance shot up. It was a huge win. But there was a ghost in the machine. You see, with all this incredible speed and power came a really subtle, but actually very dangerous, new problem. The system was fast, for sure, but was it always right? The hidden flaw, the ghost in this cache, was stale data. This is one of the most famous sayings in all of computer science, and it perfectly nails the new challenge Uber was up against. They had built this phenomenal cache, but now they had to figure out how to keep it perfectly up to date. And that is the notoriously difficult problem of cache invalidation. So here's the problem in a nutshell. What happens when the real data, the source of truth in the main database, gets updated? Well, for a brief moment, the cache might still be holding on to the old, outdated information. You might see the wrong price for a trip or the wrong status for your Uber Eats order. It's exactly like picking up yesterday's newspaper and thinking you're reading today's headlines. It looks right, but it's wrong. And this wasn't just one simple bug. It was actually 4 different problems all at once. Data could go stale because of simple network delays, or because the update message just failed entirely. You could even have these weird race conditions where old data overwrites brand new data. It was complex, and fixing it was going to require a total rethink of their strategy. And this is where we get to the aha moment. This is the real breakthrough. The team didn't just try to patch the old system. Nope, they went all the way back to the drawing board and engineered an absolutely brilliant solution. CacheFront v2. So what they did was make this fundamental philosophical leap. Version 1 was what you'd call eventually consistent. It basically said,
hey, an update happened in the database, so I'll get around to updating the cache eventually. But version 2 aimed for synchronous or instant consistency. The new goal was to make sure the old data in the cache was zapped at the exact same moment the database got updated, no delay. So how in the world did they pull that off? Well, it all came down to two incredibly clever changes they made deep inside the database engine itself. First, something called soft deletes. Instead of just deleting data, they'd mark it with a tombstone. It's like putting a note on it that says, "This is gone." Second, they gave every single change a unique, always increasing timestamp. Think of it like a universal clock that lets them know the exact order of every event, everywhere in the system.
All of this led to what I'd call a belt and suspenders defense system. 3 layers to be exact. Layer 1 is that instant synchronous callback. It's the front line. But just in case that fails for some reason, Layer 2 is the old asynchronous system, which swoops in and cleans things up in under a second. And for the final failsafe, Layer 3 is just a simple timer that automatically expires the data after a while. It's just an incredibly robust design.
So, they built this incredible new system. But the million-dollar question is, did it actually work? Well, this final section is all about the payoff. And trust me, the numbers are just jaw-dropping.
Okay, first things first, they had to be absolutely sure it was working. There's a famous saying in engineering, you can't improve what you can't measure. So they built a special tool called the Cache Inspector. What it did was constantly compare the data in the cache against the true data in the database, giving them a real-time dashboard of exactly how stale, or hopefully how fresh, their data was.
And the results that came back from the inspector were just, wow. The new system had a cache hit rate of over 99.9%. That means almost every single request was being served at lightning speed from the cache. And at the same time, data staleness was kept below 0.01%. It was so effective, so reliable that they could confidently let data live in the cache for up to 24 hours.
And here it is, the ultimate punchline. The new, more consistent system wasn't just more reliable. It turned out to be way more scalable. It completely unlocked the system's potential, pushing it to its new peak, 150 million reads per second. That's nearly a 4 times improvement over the first version.
And this wasn't just about some abstract big number. The experience for you, the person using the app, got so much better. Latency, that's the time it takes for the app to respond, it just plummeted. For most users, response times went down by 75%, and even for the slowest 1% of requests, it was cut by over 2/3. The system was bigger, more reliable, and way faster.
And let's not forget why they started this whole journey in the first place. We're back to the cost savings. Remember that workload that would have taken 60,000 database cores? Well, it's still being served by just 3,000 cache cores. That 20-fold efficiency gain held true, proving this solution wasn't just a technical marvel, it was a massive economic win too.
So in the end, Uber's engineers didn't just build a bigger system, they built a smarter one. And they managed to solve one of the hardest, most classic problems in computer science along the way. It really just leaves you with one final thought. They conquered 150 million requests a second. What kind of new thinking, what new breakthroughs will it take to get to the next frontier? 1 trillion.